All right, next up is derivative rules. When we first introduced slopes equaling how quickly things are changing. Okay. And we start with just our simple slope, which are of a function. We started with just functions, where you take the difference of your y's and divide it by your x's. You get this y's per x idea. If you divide the two, you can have like y's per 1x. So this is an average rate of change. Average rate of change is just the slope of 2 points connected with each other, slope of the secant. And we would say on average, the function is increasing or decreasing based on whether this is positive or negative, this many y's per x over an interval, wherever the interval is. And then we talked about how we could find the slope at a point, or the instantaneous rate of change. And we said, well, Newton says it's like, well, if slopes are change, all we have to do is kind of look at the slope at 1 point. But how do you find the slope at 1 point? You need 2 points. And he says, well, why don't we just attach a limit to this? And we marry a limit to a slope formula. And as long as x1 is approaching x2, then the 2 points are going to be really close together. This is why we learned about limits. We learned about the idea of getting really, really close to something. And boom, this becomes an instantaneous rate of change. And we would then say at x equals x2, f of x is increasing or decreasing this many y's per x. And usually doesn't look like that. It's usually not a y2 minus a y1. Rather, we say there's an x distance h that is approaching 0. This is x2 minus x1. And then this would be a y2 minus a y1. Okay? And if you see something like this, you should know that this is just like, hey, what is the rate of change of the sine function at an x value? What is the rate of change, the instantaneous rate of change of the sine function at an x value? If you saw this with a pi over 2, you would find it's what's the instantaneous rate of change of the sine function at pi over 2. And we realize that there are equations that are slope equations. We call them derivatives. It's like if we have a function and it looks like this, then we can know that we have x's and y's. Why don't we graph their m's? The m's of f of x, the slopes. So we get the idea of like an xm graph. And you can see like the slope is super negative, less negative 0, negative, less negative 0. We have like a positive slope here until another 0 slope. And then all of a sudden we realize that we got negative slopes, negative. All of a sudden we realize that the slopes make a graph. And if we have an f, our goal is to find the f prime equation so that we can plug in an x and get an m. So this is kind of like what I did with sine. The slopes of sine at x values will be given by the cosine function. This is called the derivative. This is y prime. This is y's slopes. You don't say it's y1. You say it's y prime. And y prime is the slopes of y at an x value. Okay? So remember, you have to plug in x's to get m's. You plug in x's to get y's into this. You plug in x's to get m's. We learned the power rule, where if your equation is some polynomial, that its slopes will be given by 1 degree less times a constant. That actually comes from the binomial theorem. We talked about products, quotients, chains. Probably the one I want to talk about is the chain rule. And the chain rule, what we say is we use an O and I, and we say, and most of my students are very good at this, we don't have to worry about it. It's like if you have a composition of multiple functions, to take the derivative and multiply the products of the derivatives of the components, getting you that the slopes of y at x will be -8 times 3 minus 2x cubed. What starts in the parentheses stays in the parentheses. That, my friends, is derivatives. All right? They challenge you to understand what differentiability means. Differentiability means not only do we meet up or continuous, but we meet up smoothly. This is the idea of when we not only check by plugging in 3 into both, and we get 9 equals 18 minus 9, 9. So we are continuous. We are continuous. Cool. So that checks out. But we also have to make sure that the slopes meet up. This is where we look at the slope of both of our pieces. And we realize that, yes, both the function values to the left and right of 3 are correct. 18 minus 9 is 9, so that's good. 3 squares 9. And the slopes, so this is the f of x's, and the f primes also are the same. So we are actually differentiable. If you're differentiable, it applies in continuous. You didn't have to say both continuous and differentiable. Okay. Here, this is the idea of the marriage of the slope formula and the limit. You're looking for like slope as like 2 points are approaching the same point. We're looking for like the slope at A. So this is the idea of a y2 minus a y1 over an x distance, x2 minus x1. This distance on the bottom should be getting close to 0. The y's should be getting close to the same value. And yes, this is actually, that's correct. That checks out. This is also going to be something like 2 points getting infinitely close to the same location at A. This also checks out. This one doesn't check out because if I plugged in A, as I get closer and closer to A, I get f of A plus h minus f of A over h, and that doesn't give me 0 over 0. So this one's actually just like a fake out. It looks like it is the marriage of slope and limit, but it's not in a way for us to get a slope where the x1 approaches the x2, which means the y1 will be approaching the y2. So there's just 1 and 2. Okay. Where are we not differentiable? Wherever we have a jump, wherever we have a vertical tangent, we don't have a tangent slope. So 0 and 2. So if like f prime is undefined, that means f prime like does not exist. If you ever have a vertical tangent, you have one like a number over 0. You don't have a derivative there. Like, yes, you know what it is. It is the location of a vertical tangent, but vertical tangents we say are locations where we're not differentiable. That's kind of tough to understand because we've been asked to find locations of vertical tangents, but turns out like we would say that's something that's not differentiable. All right, cool. If we have the graph of f, what would be the graph of its slopes? Well, we could see we have a 0 slope really there. We have this very lightly positive value that gets more positive and then less positive. So it looks like we're going there. We have a 0 slope right here. And then we got negatives, but then we get a little bit less negative. A little less negative. So I'm thinking we have something like this. So very similar to this one with the 0 right there. Yeah. Okay, same deal. We can see we have 2 0 slopes. Again, this is x's and y's. Let's do x's and m's. We have positives, less positive 0. We have negatives, back to another 0, then positives. This is like when we first said, like, hey, there is the existence of an equation that would give you the slopes of y. This is where we started, like, what is this f prime? It's like, well, it is the equation that can give us the slopes of f. If this is f, is this f prime? Yeah, that kind of checks out. We got this positive, more positive, more positive, positive, more positive. Here we got positive. Hold on, that doesn't check out. Positive, this should be a 0. There should be a 0 here. That does not check out. This is positive. There's a 0. This is negative, positive. Okay, so 1 and 3 check out. The sun is going down. Okay, this is tricky. So this equation is y equals 3/4 x. I subtracted 3x divided by negative. He said this is tangent to the, in the first quadrant to this curve. Then what's k? Well, the key to these problems is that you need to share two things. You need to share a slope, first of all. So we know that the slopes of x cubed plus k are 3x squared. Well, 3x squared has to equal 3/4 somewhere. And I realize that that's when x squared equals 1/4, when x equals plus or minus a half. We're looking in the first quadrant, so I'm going to go with positive a half. Oh, that's not that bad, but that's an x coordinate. Now, we got this x coordinate. I don't want to select 1/2 because I'm trying to find k. Well, how do we find k? Well, the other thing that they need to share, this is them sharing slopes, but they also need to share like a y coordinate point. So when x is a half, y is 3/8. When x is a half here, y is 1/8 plus k. K has to be equal to 2/8, which is 1/4. And that question's a little bit on the upper level of difficulty, but I don't know, maybe they start showing it. We haven't seen an actual multiple choice test in a while. Don't forget about OMI. Don't forget about parentheses. This is actually an outside, middle, inside. Outside is the square, middle is the cosine, inside is the 3x. Outside slopes are 2 parentheses, middle slopes are negative sine parentheses, inside are 3. Multiply them all together, I'd get -6, big parentheses. What starts in that big parentheses stays in the parentheses. And then I'd have a sign. I already put the negative in front of the 6. What starts in the parentheses stays in the parentheses. So -6 cos 3x sin 3x. Quotient rule, slopes of the top times the bottom. Slopes of the bottom times the top. All over the bottom squared. If I plug in 1, f prime of 1 is 2 minus 0 over 2 squared. So that's 1/2. Slopes of x are 1. Slopes of sine are cosine. Slopes of cosine are negative sine. If the derivative of f is g, the derivative of g is f of x squared, what is the second derivative of f of x cubed? Haha. This one's tricky. We start with f of x cubed, and we take the derivative of this using an O and an I, and I got an f parentheses and an x cubed, and I got f prime parentheses, and I got 3x squared. So the first derivative is f prime of x cubed times 3x squared. And you could say that f prime equals g, but I'm going to leave it like that. And now I'm going to take the derivative of that. But you know what? I'm literally seeing this already, that f prime needs to be g. So I'm going to write it like this. Now, if I'm going to take the derivative of this, I need to not only use the product rule, but use the product rule and the chain rule. A lot of people mess up when on the first iteration of a derivative, you use one rule, and then on a second iteration, you do like 2 different rules. You have a chain and a product. So we got an O and an I, so the derivative of the first is g prime of x cubed times 3x squared. That's the derivative of the outside. times the derivative inside, so derivative of the first times the second, plus the derivative of the second times the first. And I'm just told that the derivative of x cubed is f of x squared. So the derivative of x cubed is f of x squared. But I have x cubed. So I need f of x cubed squared, which gives me f of x to the sixth. This is also a little bit tricky. This is 9x to the fourth. This is 6x g of x cubed. So, oh, look at that. Oh boy. Oh. I mean, this one is probably the only one that makes sense to be correct, but maybe you don't see that. That was challenging. Do you have to use the quotient rule? No, not always. Sometimes you could rewrite things and use the chain rule. Watch this. I'm going to rewrite this as 3 times 4 plus x squared to the negative first. This is what you have to do for anything in a denominator. Don't use the power rule in a denominator. Use the quotient rule. If you took the derivative of this, not using the quotient rule, you get the derivative of the outside, which is that, times the derivative of the inside, which is that, which means you get negative 6x, 4 plus x squared to the negative second. Negative 6x, 4 plus x squared to the negative second. Notational derivatives, like the derivative of f is f's slopes. So the derivative of f of g is an O and I. It's an f parentheses, it's g of x. Slopes of f are the slopes of f. The slopes of g of x are the slopes of g of x. We don't have to do an OMI because the slopes of x are just 1. It's like whenever I say, what is f of x slopes? We don't have to use the chain rule. We say it's f of x's slopes. Anyways, that gives you h prime is equal to the slopes of f with g of x values times the slopes of g. If I'm plugging in 1, I get f prime of g of 1. G of 1 is 2. I get g prime of 1. G prime of 1 is negative 3. So I have f prime of 2 times negative 3. F prime of 2 is negative 4 times negative 3, which is 12. It's O's and I's. Same deal. So we got 2 different ones. So you take 2 different ones. So we got negative 2 cosec sine x. And then we got minus positive 2 sine x cosec. And would you look at that? Minus 4. No? I guess we're factoring out. Well, now this is interesting. Yeah, I'm sorry. This is, I think I remember this problem. I think that's the answer. Yo, skip this problem. Why? You have to use the double angle formula. Let me remember the double angle formula. It's sine, cosine, cosine, sine. So it's sine x, cosine x. So it's 2 sine x cos x. So the sine of 2x equals 2 sine x cos x. If it was 4, this would be 2. And if it was negative 4, then this would be negative 2. Yeah, skip. You got this step, great. And then you have to use a double angle formula from there. How many questions do I have left? All right, we gotta plow through. Might have to back up. It's getting cold. My face is getting cut off by the sun. Backing up. Oh yeah. Whoa. Oops. All right. If I'm taking the derivative of 1 over x cubed, I'm starting as x to the negative third. Or I'm using the quotient rule, but it takes too long. So I'm bringing the exponent down, subtracting 1. I got negative 3x to the negative fourth. I'm writing this as x to the negative first, bringing the exponent down, subtracting 1. So that minus the negative becomes plus a positive x to the negative second. And then x squared is 2x. So this is y prime. And if I'm plugging in negative 1, I have negative 3 plus 1 plus negative 2. So negative 5 plus 1 is negative 4. Cool. Thanks for giving me the point, guys. It's a product and a chain. Multiple rules. Slopes of the first times the second. Plus the slopes of the second. O and I it if you need to. Times the first. Plugging in 1. I'll get negative 1 plus negative 6, which is negative 7. So I got y plus 1 equals negative 7, x minus 1. It's got to be this. Let's just double check. Cool. Another O and I. Square roots, you write it as a 1/2 power. O and I it, you get 1/2 to the negative 1/2 and 2. The 2 and the 1 go away. So you got 2x to the negative 1/2. So that becomes 4 to the negative 1/2 at 2. And that's 1 over 4 to the positive 1/2. So that's 1/2. X over 2 is the same as 1/2 x. Tell you that over and over again. Don't let this mess you up. So the first derivative would be negative cosine x over 2, because the negative 2 and the 1/2 would cancel. The second derivative, therefore, would be positive 1/2 sine x over 2. Go ahead and O and I it. The O being the negative cosine, the I being 1/2 x. Negative cosine slopes are positive sine. 1/2 x's slopes are 1/2. So that's that. And now I have my answer. 1/2 sine x over 2. Shoot. It's a sine. Oops. Which means keep the negative. Negative 1/2 cosine x over 2. Oh, this is tricky. It's a quotient, but as part of the quotient, you have a product. So slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. u prime v w, u prime v w, u v prime w, u v w prime minus. Yeah, so there you go. There it is. This is just the combination of the slope formula and a limit, saying what is the slope of sine at x. The slope of sine at x is cosine, like at x. Plug in values into cosine, you get the slope of sine at that value. Slopes of the top times the bottom minus the slopes of the bottom times the top over the bottom squared. Do you have to simplify this? Nah, like I got a point, so I might as well plug it in. Don't simplify unless you really have to. Just looking for an equation. I got y minus 5 equals negative 13x minus 1. We want everything on one side. It's like, how do you write equations in standard form? I honestly don't know. What they're going to say at the start rage on. Cold and follow me in. It's funny how some distance makes everything seem small, and the fears that once controlled me can't get to me at all. My daughter's now old enough where Frozen is like lame. It's like, oh, I hate Frozen. It's like, Frozen's great. Okay, Lola, we will continue to watch Frozen and appreciate Frozen because it's good. Let it go. And the ones when we got done. Oh, I don't know. Let it go. See me cry. Here I stand, and here I stand. At the storm rage on. You put it. A power flurries through the air into the good. We're spiraling in frozen fractals all around. And one God crystallizes like an empty shell. I'm never going back. The past is in the past. Let it go. All right. Why is it this? How do I remember this? It's because like e to the x could have a log e afterwards, but the log of e is just 1, which is why like we don't use it. We just say it's e to the x. That's how I remember it. C. This is actually unit 4, but whatever. That guy gets it. This is another product and chain. I'm sorry for all these product chain rules. So like every time you take the derivative of the second piece, you got to use a chain. So let's O and I for the second piece. Girls in Lola's class are starting to get mean already. And she's in 3rd grade. There's already mean girls who are bullying. Slopes of the first times second plus the slopes of the second. The 1/2 and the 2 cancel times the first. Not plugging in anything. We get root 2x minus 3 plus x over root 2x minus 3. I don't see that anywhere. Why? Because, these questions are fine, but not great. We're going to have to somehow combine these two. You're going to multiply the top and the bottom by root 2x minus 3 to get the common denominator so you can add things together. And when you do that, you get 2x minus 3 plus x over root 2x minus 3. And that's 3x minus 3 over root 2x minus 3. Wow, there's a lot of questions from this unit too. All right, finishing strong. Come on, what?
Is it a...
Yeah, we're doing a calculus video.
No way.
Yeah, you just photobombed a calculus video.
No way.
All the seniors are going to be like, who's that kid?
I bet like one person mentioned this.
Yeah.
You got Ruben in your class?
Yes, I do. Are you working on the no calculator part?
Yep.
Okay.
Is it more?
Do you know?
Are you live?
Yes. No, I mean I'm not streaming. Like this is recorded.
Are you gonna like edit it?
Do you know the 30, 60, 90 triangle?
Yeah.
All right, then you're fine. And you know the 45, 45, 90?
Yeah.
All right, then you're fine. Again, OMI. Again. There's a lot of practice for these derivative rules. But like, unfortunately, or fortunately, I don't know, wherever you stand. There's a lot of questions about derivative rules on the actual AP exam. Lots of 1, 2, and 3 questions. Unit 4, Unit 5. Good stuff. Tricky stuff. But not as important as Units 1 and 2 and 3. Okay, so I got -6 cosine. I feel like I did this problem already. X cubed times sine x cubed. X squared. You may get some reason, students with cosine 2x, they forget about the 2. They think it's so simple that they don't need to use the chain rule, but they very much do. This is the slope equation. I'm going to plug in pi over 4 to get the slope of cos 2x at pi over 4. To get -2 sine pi over 2. Cool, because pi over 4 times 2 is pi over 2. Sine of pi over 2 is 1, so I get -2. Cool. And then we have the y coordinate. I haven't done this yet, but don't forget to plug in x into the original equation to get the y. And this gives you 0, which means you get y minus 0 equals m times x minus pi over 4, not pi over 2. At what point on the graph of this is the tangent line parallel to this? I like this question. This is more realistic. It's not as hard. You need to know the slope of this. This equation is easy enough to solve for y. Well, you get the slope of this line as a half. You're trying to figure out when this has a slope of a half. It's a great question. Wish we had more of these because it's very like basic. Parallel lines equal slopes. This is the equation of the slopes. It's that simple. It's just x. 1/2 x squared slopes are given to us by x. When does that slope equal a half? When x equals a half. That's a little bit funky. When x is a half, what is the y coordinate? Well, that's a half squared, which is the 4th times a half, which is an 1/8. So that's the point. If the rate of change of f is twice the rate of change at 1, then c equals. So the slope at c is twice the slope at 1. All right, cool. But first of all, you've realized rate of change means the slope. So you need the slope equation. and you need the slope equation at 1. You need the slope is 1/2. So the rate of change at C is twice the rate of change at 1. The rate of change at C is 1. When do the slopes equal 1? Well, I'm going to go ahead and flip both sides, divide by 2. That's when root x equals 1/2. And then I square both sides and I get x is 1/4. Cool. Yeah, it's like earlier the square root is steeper than later. So the rate of change earlier is going to be greater than the rate of change later because the square root graph goes like that. This is the graph of f prime. 3, 5 is on the graph of f. Well, f prime of 3 is 2. This is another great question. F prime of 3 is 2. So y minus 5 equals 2, x minus 3. It's a great question. Do you really understand what you're looking at? What you're going to do? Good with that. Great question. It's not 0. This is the graph of the slopes. This is not the graph of f. This is going to be very important for unit 3, which we're coming up to soon. We got these 2 points. We're guaranteed to have a y-coordinate between -3 for all x's between -3 and 6. So the y-coordinates don't have to be between -1 and 3, but we must have at least one solution between -3 and 6 to get the y-coordinate of 1. Let me just walk you through all of this. You got the point -3, -1. You got the point 6, 3. Okay. All you have to know is that these 2 points connect somehow. Must you have the point 0, 0? No. Could you have 0, 0? Sure. Must you? No. Must the slope equal 4/9? Well, yes. This is a yes, but this is a mean value theorem question. This is a yes if the function is differentiable. You are not told that the function is differentiable, which means it's continuous and smooth. You're just told that it's continuous. So this would be a mean value theorem statement, which would be yes if we said it was differentiable, but we did not. Must all the y values be between -1 and 3? Well, this is the idea of like, yeah, probably they'll be between -1 and 3, but you don't have to be. Your 2 points can be connected like this, and here are y values that are less than -1. So this is not necessarily true. If you go below -1 or above 3, then your y values are not all between -1 and 3. It is very windy right now. Between the x coordinates of -1 and 3 or the x coordinates of -3 and 6. That's the only way to distinguish the last two. Is that we're talking about the x coordinates, -3 and 6, not between the y coordinates. Happy to talk you through that one if you guys want to come in and ask questions about it. But I got to go inside. It's freezing. Peace.